Let's kick off this very exciting section of this course by talking about internet protocols, what is the internet, and we're going to do so with this mega lecture on everything that we're going to need throughout the next two sections to become an extremely competitive system administrator. And before we start, we have to define what's the internet. And the internet is basically a collection of devices, so hardware, and protocols and their implementations, so protocols and software that allows two or more devices to exchange information over a public network. We can see the internet as organized in 7 layers, and this is how the OSI stack is played out. So we have a physical layer, a data link layer, a network layer, and a transport layer, which is going to be the focus of this section and the next section, where we're going to briefly talk about layer 5 and layer 6, but we're going to see a lot of applications on layer 7, for example, web servers, SSH protocol, and whatnot that sits on top of the stack. Now, the physical layer is perhaps the least interesting thing from a system administrator perspective, because the physical layer has to do with all the electronics, the devices, the cables that are going to be used to transmit raw bit streams over like the physical medium, which can be like the air, if we're talking, for example, Wi-Fi, or a cable if we're talking Ethernet and whatnot. So we're going to start our discussion from layer 2, where we start talking about protocols. Basically, the epitome of layer 2 is the Ethernet protocol. And Ethernet was a protocol that was invented in 1973 and has evolved up until our days, where we can reach 100 gigabits per second over a single fiber optic cable. And the physical medium of Ethernet has changed quite a while over the years. At the beginning was coaxial cable, then we had twisted pair, then we started having these RG45 cables that everyone has. They are an evolution of twisted pair. They usually contain 8. There was more technology advancement around the shielding of those cables and whatnot, but the real breakthrough happened when fiber optics came around and the ability to drive those fiber optics cable with a laser. And so that unlocked like tens and hundreds of gigabits per second over long distances and a single fiber optic cable. But Ethernet is a layer 2 protocol, and what Ethernet does, it defines a frame format. And Ethernet is also known as IEEE 802.3, and that's the formal definition of the standard. But this is what we send over the improperly called Ethernet cable whenever we send out an Ethernet frame. So there's a preamble and a start frame delimiter, and this is pretty much transparent at the end user, meaning that each packet has the same one, so it does not contain information, but it's just needed for the device and router, device and device, to tell to each other, hey, I'm about to send an Ethernet frame. So we have a preamble, a start frame delimiter, then we have a destination MAC address. And MAC stands for Medium Access Control, and it's basically a 48-bit, a 6-byte address for which this Ethernet frame is destined to. Then there are other 48 bits, 6 bytes of the source MAC address of the station that is sending out this Ethernet frame. And then we have 2 bytes that describe the length of the payload of the data that is going to be attached to this Ethernet frame, which is typically between 46 and 1500 bytes. And this 1500 bytes is also called the maximum transfer unit, so MTU. And then we have a frame check sequence, which is basically a CRC of the entire frame, because we may have errors in the forwarding of this frame, and we want to be able to detect them. This is not a SecDet code, so we're not able to correct any error, but at least we can detect it, and Ethernet has a mechanism for sending back a packet and say, hey, the packet you just sent me came back with an error, send it back again. The interface between layer 2, so the Ethernet protocol, and layer 1, so the actual cable that connects to devices, is the network interface card. And the network interface card is the physical device in which you either plug the cable for Ethernet or provides radio access to the medium for Wi-Fi. And the network interface card interacts with the operating system via device drivers. And the OS can virtualize NICs, meaning that you can manage a network interface card that do not correspond to physical devices, meaning we can abstract from the actual network interface cards. We can create virtual network interface cards with different MAC addresses that then map to a single card. And we will see how this is going to play out when we are doing top devices. But in Linux, the naming scheme for Ethernet interfaces was ATH-X, where X is an index. Today is slightly changed, but we're going to see in the framework that we're going to use, it's still going to be ATH and an index. So we talked about the MAC address, and you typically found it printed in 6 bytes hexadecimal format separated by double dots. And the first half of the MAC address is the organizationally unique identifier, and this typically identifies the manufacturer of that device. So for example, all the network interface cards by Intel are going to have the same upper 24 bits, while the last 24 bits, Intel can assign it the way it wants. For example, it can be a serial number, or it can be whatever the manufacturer wants, but these upper 24 bits are like globally known, and they have to be assigned by the IEEE committee if you want to build out Ethernet appliances, Ethernet devices. There are a couple special addresses, and the most important one is going to be the broadcast one. Whenever we put all Fs into a destination MAC address, that frame is going to be intended to all the devices that are inside the same broadcast domain. We're going to see what that broadcast domain is, but basically it means that that frame is intended to everybody that is listening. And we're going to see that those broadcast frame play a huge role in protocols like the ACP and ARP and all those protocols that we're going to see during this section. The way we connect multiple devices together in Ethernet has evolved quite a while since the beginning, because a network is composed by multiple devices. And let's take the hub, which is the first network aggregator that we had historically. It is a physical layer device, meaning it is not a layer 2 device, but what it does is takes the electrical signal of one station and repeats it, restores it, but it does not apply any kind of intelligence to the forwarding of Ethernet frames. Meaning that if, for example, this station is sending out something to another station, nobody else can send anything. Otherwise, we have a collision on the network, and Ethernet is a carrier sense multiple access collision detection protocol, meaning that it has mechanism to detect a collision and has a retransmission algorithm which is called exponential backoff. So what happens when we have a collision is that we stop transmitting and we try and retransmit after an exponential time. But the problem with the hub is that we have a single collision domain. So we only have half duplex operation. We cannot be transmitting and receiving at the same time because the hub doesn't support that. The bandwidth is shared across all the stations that are, all the devices that are on this hub. There's no intelligence, no frame buffering, simply repeat bits. The problem is that as we attach more station, more devices to the hub, we increase the possibility of collisions, so the effective bandwidth decreases significantly. And there are security concerns, meaning that since the hub doesn't apply any kind of forwarding mechanism, the signal from this station to this other station gets repeated to all the other ports. So it's like there is some sort of promiscuity in the operation of the hub. And so there are some security concerns, meaning that now what was intended only between this guy and this guy gets listened also by those two guys. But this was the best we got. Up until the switch came around, which is typically what you have inside for routers at your home and what you can typically buy. I don't think you can buy a hub anymore. And this is a data link layer device. It's a layer 2. Each port is a separate collision domain. It supports full duplex operation. It has a dedicated bandwidth per port, meaning that if there's a 1 gigabit switch, means that each port gets 1 gigabit bandwidth. Has frame buffering and forwarding. It has this algorithm that is called MAC address learning, and this is how the switch learns what stations are behind each port and make sure to forward the appropriate frames only to the intended receivers. And in fact, we do not have no collisions, better for performance scalability and enhanced security. And also, we have separate collision domains, but a single broadcast domain, meaning that if one station sends out a broadcast frame, it gets received by everyone. So this is the difference between a collision domain and a broadcast domain. A collision domain is everywhere that I can have collisions, so everywhere that I can have two hosts transmitting at the same time and disrupting each other's transmissions. So whenever we have a hub that builds up a collision domain, this is another collision domain, but the switch segments the network into different collision domains. But if a broadcast frame is sent by this upper laptop on the right, it gets received also on the other collision domain. And we're going to talk a lot about collision domains during the course of this section. So we talked about MAC address learning, and what it is basically the algorithm that the switch runs, and it's constantly running to learn the MAC addresses that are behind each port of the switch. And the purpose of this algorithm is to basically build what is called the forwarding table to make smart forwarding decisions. And the learning algorithm is extremely simple. So suppose that a station sends out an Ethernet frame. This Ethernet frame reaches the switch. The switch can now examine the source MAC address of that packet and say, hey, behind this port, there's this MAC address because I received a frame with source MAC address this one. So it builds inside its forwarding table port A MAC address X. It sets an age, a timestamp for that entry, and the timestamp, it really depends on the switch implementation. And then it forwards the packet. And there are really two cases for forwarding the packet. If the destination MAC is already in the forwarding table, the switch forwards the frame only to the specific port where the destination device is. If the destination MAC address is not present in the forwarding table, the switch will flood all the ports except the source port, because the source cannot be the destination as well. And also there is a refresh of the entries inside the forwarding table. Frame types can be unknown unicast, meaning unicast is whenever we have a device wanting to talk to another device, and whenever it's unknown, we just flow the network, knowing that when the user replies, we will learn its MAC address, so the next time that station needs to talk to the other station, we have a forwarding entry for both the source and the destination, so we don't have to float anymore. A known unicast, there's a hit on the forwarding table, so we forward to a specific port, and if it's a broadcast or a multicast frame, so broadcast, remember, destination address, all Fs, we float to all ports. And so this is how it works. Suppose that we have station A, B, C, and D attached to a switch, and A is attached to port 1, B port 2, C port 3, and D port 4. We just plug on the switch. The forwarding table of the switch is empty. A sends a frame to C. And what it does is the switch learns that the MAC address of A is behind port 1. But since it does not have an entry for C, it floats the packets to port 2, 3, and 4. Behind port 3, there's C that replies to that frame. And at that point, the switch learns that behind port 3, there's MAC C. But since the switch learned in step 1 the MAC address and port association for A, now the forwarding happens to just to port 1, because the switch knows already how to reach port 1. And this is the final forwarding table, where we have an association for A and port 1 made in step 1, and an association for C and port 3 made in step 2. So there are key elements that happen like automatically inside the switch, which is dynamic learning, aging, floating if we don't know the destination. We have to detect loops inside the network, because otherwise that's going to blow up our forwarding table. So it requires what is called a spanning tree protocol, and that's quite heavy in terms of computation. How big is the forwarding table for a switch? It really depends on how much the switch costs, because a forwarding table is typically implemented with what is called content addressable memory, and this is extremely expensive memory. So enterprise switches that cost like hundreds or thousands of dollars can range between 8K to 128K entries, meaning they can record 128,000 devices, port associations in any given moment. And the default aging time is still 200 seconds, 5 minutes. There are some security implications, meaning that the association between a MAC address and a port is not, let's say, authenticated, meaning that it's dynamically learned. So if somebody can impersonate another MAC address and make the switch believe that that MAC address is behind a port, while in reality it's in another port. And that's called MAC spoofing. And it's the basis for man-in-the-middle attacks. This is something that it's covered in another course of mine. But let's say behind this extremely smart and simple operation of the switch, there are a lot of security implications. And so this is why for some enterprise switches, it is recommended to have static MAC entries for critical devices, because the MAC address is not going to change unless you change the network interface card, and the port association does not change unless we go there and unplug the cable from one port of the switch and replug it somewhere else. So MAC address and port association should be fairly static for critical devices. Now we know everything there's to know about layer 2 addressing and how layer 2 switching works. The problem with layer 2 is that it's a local area network infrastructure. So what about routing between local area networks? So we have to move up a layer onto the OSI stack and go on to layer 3. And the key responsibilities for layer 3 are logical addressing, routing between networks, path determination, packet forwarding, fragmentation, and reassembly. We're going to see what that means with the concept of MTU, maximum transfer unit. So here we got the key functions. We got routing, so path selection across networks, routing table maintenance, which is going to be kind of similar to the MAC table that the switch maintains. Next hop determination, so who's going to be the next device on the network that I'm going to forward my packet to that knows how to reach my final destination. Load balancing, then addressing, hierarchical addressing scheme. We're going to see what that means with the concept of network address translation, network and host identification, subnetting, and address resolution with the DNS and whatnot, packet processing, and quality of service. So these are layer 3 key functions. And one of the main protocols that live on layer 3 is IPv4. And this is the header structure of an IPv4 packet. Remember, in layer 2 LAN, we talk about frames. In layer 3 LAN, we talk about packets. And this packet, it's going to be inserted inside a layer 2 frame when reaching the local area network. And this is how the header is structured. We've got a version, we got a few other flags, the total length of the packet, the sequence number, flags, fragmentation, time to live, protocol that is going to be transported by this packet, the header checksum, source IP address, destination IP address, options padding if needed, and then the data that's going to be transported by this packet. So what's the difference between IPv4, which is layer 3, and layer 2 addressing? So the scope, of course, it's local network segment, while layer 3 is the global internet. The structure is flat. We use a 48-bit MAC address on layer 2, while on layer 3 we use a 32-bit IPv4 address that is going to be hierarchically managed. The assignment of the MAC address is going to be fixed by the hardware manufacturer, while it's your job to set up the IP address. The MAC address is assigned to the network interface card. It cannot be changed, while the IP address is of course configurable. In terms of routing, so the ability to reach that address from other devices onto the global internet, of course a MAC address is not routable, while an IP address, it's fully routable. And this is the difference in how we write MAC addresses and IP addresses. So why we need layer 3? MAC addresses only work within broadcast domains, so we cannot extend switches all over the place. We need a hierarchical addressing for scalable routing, logical separation from the physical hardware, and it enables internetworking between different technologies. So we don't need to rely only on Ethernet, but maybe we want to go over Wi-Fi, or we want to go over GPON, which is fiber optics, and other technologies that do not necessarily fall into the Ethernet category. This is the IPv4 address structure, and I'm sure you've seen it. It's a 32-bit address space divided into 4 octets, and they're typically printed out in decimal, and they are separated by dots. Each octet can go from 0 to 255 because we got an 8-bit number. And we have a hierarchical structure as network plus host portions, and we're going to explain this when we talk about the subnetting part. This is an historical way of viewing the IPv4 addresses, where we fix the first octet and then we let the other bits change. The problem is that it was an extremely wasteful allocation, limited flexibility, and we had really huge troubles scaling this approach to the whole internet. So a solution was the classless inter-domain routing. So we moved away from classes and we landed on the concept of subnet masks. And this is what it looks like. We got a subnet, which is identified by an octet, /24, which tells us how deep is the prefix and how many hosts we can have on that subnet. So for example, here we got 192.168.1.0/24. It means that we got this subnet mask. And if we AND logically this thing with this thing, we got the first octet that it's free. So it means that we got 256 addresses that we can assign to hosts. The reality is that we can use 254 of them because 255 it's going to be reserved for the broadcast IP address for that subnet, and the .0 already identifies the subnet. The same thing goes for /25. We got this subnet mask, so it means that we have at most 128 addresses, which is the difference between 255 and the 128 that we got here. But only 2 of them are usable, again, because 127 is going to be the broadcast address for that subnet, and the 0 is going to identify the subnet. And we got 192 that allows us 255 minus 192, 64 addresses. The reality is that we only have 60 usable. And the same thing goes for /30. We're going to see that we are going to be able to use a /31, where in theory, if we follow this approach, we're not going to be able to use any address because a /31 is going to have only 2 addresses. But if we assign one to the subnet and one to the broadcast, we're left with 0 addresses that are assignable to hosts. But in that case, we make an exception. There's actually an RFC out there that says when you only have 2 hosts on a subnet, so /31 means we only have 2 hosts, there's really no point in identifying the subnet and a broadcast domain. It's either one host or the other. That's where we kind of break this rule, but we're going to see that into the OSPF lecture. So here we have a few guidelines on how to assign IP addresses, and we're going to make a difference between private and public IP addresses, and we're going to explain what that means. But for now, if we want to comply with RFC 1918, this is the suggested IP address range for large enterprises with a /8, meaning that only the first octet is fixed. All the other IP addresses can be assigned to devices. Then we have for medium enterprises this one, and then for home and small offices we got this 192.168.0.0 up to 255, which is a /16. Chances are that if you look at the IP addresses that your router at home assigns to IPs, it's going to be a 192.168.1. something or .0. something. We got a few special addresses, which is 127.0.0.0/8, which is going to be localhost. The current machine, also known as loopback. We got the 0.0.0.0, which is the default route or this network. And then we got a multicast address, but we're not going to deal with that too much. So these are the 2 most important ones, the loopback and the default route. So why we need private addresses? Because we want to conserve public IPv4 address space. So we don't want our toaster that now it's connected to the internet to be fully routable from Google and to be able to access that toaster remotely from anywhere in the world. It allows to reuse the address space. It provides security through obscurity and requires network address translation for internet access. Also because we got only 4 billion roughly of IPv4 addresses that we can assign, and we are way past the 4 billion devices that are connected to the internet. If we assign a public IP address to each and every device that we have, we're going to run out of IPv4 addresses real soon. So what is a router? It's a layer 3 network device that forwards packets between different networks, makes forwarding decisions based on destination IPs, connects multiple network segments or subnets, and maintains routing tables for path determination. And so this is how the router works. It looks a lot like switch. While the switch connects different devices or different collision domains, the router connects different networks. And here we have network A, which is based on Ethernet, network B, which is based on Ethernet, and network C, which may be based on GPON, optical fiber. How does a router forwards packets? The first step is the router receives the packet on one of its interfaces, extracts the destination IP address from the header, looks up the destination routing table, determines who's the next router, also known as the next hop IP, and where the next hop lives in terms of interface. It decrements the time to leave and recalculates the checksum of the IPv4 header, performs an ARP lookup for the next hop MAC address, and we're going to see why that's needed, rewrites the layer 2 header with the new MAC address, and forwards the packet out to the appropriate interface. So the packet comes in, the router looks inside its routing table and says, okay, this packet is, for example, for 192.168.2.100. That subnet is reachable on interface 2. I'm going to take that packet, decrement the TTL, rewrite the layer 3 header, and then I'm going to go on layer 2. What is the MAC address of the router on that subnet? It's going to perform an ARP lookup to figure that out. It rewrites the L2 header and then forwards the packet. We're going to see in a few slides what that ARP lookup is, but an ARP lookup basically assigns a MAC address to an IP address. That's basically how it is. It's a layer 2 to layer 3 translation mechanism. So here we have all the difference between a router, a switch, and a hub, which are the 3 interconnect devices that we've seen so far. And we use a switch within the same network, while a router is used between different networks, as I just said. And a layer 3 switch combines switching and routing, which is typically what you have at home with your internet service provider provided router. So what's a routing table? It's a database of network destination and paths. It's stored in router memory. It's used to make forwarding decision, contains the best known path to each destination, and it's updated through either static configuration or dynamic protocols, and we're going to see both of them inside this course in a fairly detailed way. A routing table entry consists of a destination network, a subnet mask, a next hop, where that next hop is physically attached to the router, the cost or preference value of taking their route or another route if it's available, and the concept of administrative distance, which is the route sort's trustworthiness. And this is going to come into play when we are trying to differentiate between static and dynamic configured routes. This is what a routing table looks like. So here, for example, if we want to reach destination 192.168.1/24, it's directly connected. So go to R1 on 0. Probably we are the authoritative router for that subnet. That subnet is composed by different L2 switches, but we are directly attached to that. If we want to reach 192.168.2.0/24, we need to go through 10.0.0.2 on interface R2. And the cost is 1 because we have one hop to go through here, which is 10.0.0.2. And for all the other routes, so the default route is through 10.0.0.1, which is probably my internet service provider default gateway, and which is attached to R0, and the metric is 1 because I have to go through one hop. to reach the internet or all the other subnets that I want to reach. So we got a few different type of routes. We got directly attached networks, which are the most trusted, are automatically created as soon as we configure the network. Static routes, which are manually configured, are administrator defined, so it's the job of the system administrator to manually insert those routes, and we're going to see throughout this course how we're going to do that. They're reliable but not adaptive. So suppose that the default gateway changes or that link goes down for that subnet, there's no fallback mechanism. Dynamic routes are learned via routing protocols, and we're gonna, with a fair amount of detail about one, which is called OSPF, into the next section. They are automatically updated and are adaptive to network changes. And then we got a default route, which is a gateway of last resort, where we send all the packets that we weren't able to route through either directly attached routes, static routes, or dynamic routes. And it typically points to the internet service provider, where we just say, hey, I got this packet, I don't know what to do with it, just I'll give it to you, I'm sure you'll know what to do with it. If a packet comes in and it possibly matches two rules, who wins? The way we use to break the ambiguity is called longest prefix match. So the route selection algorithm finds all the routes that match the destination IP on the packet that needs to be forwarded, selects the route with the longest subnet mask, so the longest prefix, because it's going to be the most specific. If we still have a tie, use the lowest administrative distance. If we still have a tie, use the lowest metric. If it's still tied, load balance or use the first entry. This is implementation specific. But suppose that we got a packet that comes in, which is 192.168.1.150, it's going to match only this first one. So there's no ambiguity. But suppose that we get a packet for 192.168.1.50, it's going to match this one, and this one as well. So how do we know where to route? We're going to select the most specific one, which is going to be the one with the highest number on the mask, so the longest prefix. And so we're going to select 192.168.1.128/25 as the route that we're going to take, and we're going to send that packet to 10.0.0.3 as next hop. So why we use longest prefix? Because we assume that by having a longest prefix, it means that that route has been put there intentionally, is more specific, and allows hierarchical addressing, enables route summarization, and supports efficient routing table design. Now, talking about the default route, we said that we have a 0.0.0/0 destination, and this falls nicely with the longest prefix match because it matches any IP address, but since it has the lowest prefix imaginable, it's going to be matched as the last resort. So this is why we call it gateway of last resort. It's used when no more specific route exists. It typically points toward the internet or the core network, and it's essential for internet connectivity. Now, talking about static routing, and static routes are manually configured by the network administrator. They do not change unless they are manually updated. They are predictable and deterministic. They use very low CPU and bandwidth and are suitable for simple and stable networks. And this is the syntax that we have to add a static route in Linux, but no worries, we're going to have entire lectures on this. When do we use static routing? Well, in small networks, in security sensitive environments when we don't want to use dynamic protocols, and on default routes to the internet service provider. Although we don't have any automatic adaptation to failures, if that link for some reason goes down, there goes our traffic. It may have huge overheads in terms of manual maintenance. It doesn't scale at all, and there's no load balancing capabilities. So this is why we're going to see also the dynamic protocols part. And here we go with dynamic routing. And dynamic routing means that the routes are learned automatically via protocols and packets that all the routers exchange inside the network, adapts to network topology changes, automatic failover and recovery if some redundant links fall down. It scales to large networks, but requires some protocol overhead. We're going to see some packets that are flowing through the network to update those routes, and those packets will share the bandwidth of that link with usable data that flows inside the network. So it's going to steal a little bit of bandwidth, but with careful configuration, it's not going to be noticeable. And we got quite a few protocols here. We're going to talk about OSPF because it's the most used inside enterprise networks. And here we have a few benefits and drawbacks of using dynamic routing. Here's a sneak peek into what we're going to see into the next lectures if you want to see the routes that are available inside your Linux machine. And this is how we select the proper routing table entry to send a packet out. So here we're trying to send a packet to 192. We're trying to forward this packet, which has a destination address 192.168.2.50. We'll look at the routing table. This is the content of the routing table. It matches the /16, the /24. Here we have another example of route selection. Now, if we want to troubleshoot routing issues, we got some common routing problems: missing routes to destination, current next hop configuration, routing loops, asymmetric routing paths, and administrative distance conflicts where we cannot tie it off. And we're gonna go through all this troubleshooting part inside the next few lectures. Now, we talked about network address translation and what is exactly network address translation. And the purpose is to map private IP addresses to public IP addresses. The net benefit is that conserves public IPv4 addresses, provides basic security, and allows networks renumbering without external impact, and enables overlapping private address spaces. So we need to talk about a cone, right? A NAT cone. What NAT does in this example is that it takes this private network, maps all the devices, all the traffic that comes from these devices as if it comes from the router. So the public network is only going to see the public IP address of the router, which is 203.0.113.1, while that traffic may be generated by 100 or 101, like PC1 and PC2 on the private network. And it's the job of the network address translation router to keep tabs when the internet replies back to those packets, to keep tabs on whether those packets were generated by PC1 or PC2, and to de-NAT them and forward them correctly on layer 2 at this point, because we are on a private network. We got a few types of NATs. We got static NAT, where we map one private and one public IP address. It's bidirectional, and it's typically used for servers. Dynamic NAT, we got a pool of public addresses that will be assigned on a first come, first served basis. It's one-to-one at any time. Sessions might be initiated internally. We don't use that often. This is one that we're going to use, definitely, which is the one that I explained, many-to-one mapping. It relies on the use of ports, and we're going to see when we're going to talk about in this lecture about TCP and UDP what ports are. And it's the most common in home and small office and home offices, and also large enterprise for that matter, and overloads single public IP. So what I just explained, where we take one public IP address and we map it into multiple, ideally 256 here, private IP addresses. There are some limitations to network address translation. In fact, it breaks end-to-end connectivity principle, meaning that now the internet believes that it's talking to the router, when the reality is that that traffic has been generated by a private device. It creates issues with protocols embedding IP addresses, especially FTP. And there's also a port exhaustion problem with 65K ports per public IP, because we only have 16 bits we're going to see in TCP, and UDP we only have 16 bits for defining a port. So it means that if we have a very large network behind a net router, we're not going to be able to support more than 64K connections at a time. We got a few solutions and workarounds with port forwarding, which is static mapping for servers, automatic port mapping, NAT traversal for real-time applications, and application layer gateways. But those are protocol specific, and it really depends on what services are we running behind the NAT. We saw that the limitation of IPv4 and the reason why we need to use network address translation is because we will run out of addresses if all addresses were public addresses. So the basic idea is, why don't we define a protocol that extends the IP address from 32-bit to, let's say, 64. Let's double it down. And this is where IPv6 is born. It has a massive address space, has a simplified header format. There's no network address translation concept. Everything is fully routable. It has better multicast support and auto configuration capabilities. So this is what an IPv6 address looks like. It has a 128-bit address, so it's 4 times as big as IPv4. We print it as an 8 groups of 4 hexadecimal digit, and we got quite a few address types like unicast, multicast, and anycast, which are used for one-to-one, one-to-many, one-to-nearest of many forms of communication. Now, I won't go into any more details about IPv6 because typically you're going to deal with enterprise networks, which are still going to be based on IPv4. But one thing that I've hinted to when talking about routing is ARP. And ARP stands for Address Resolution Protocol and tries to solve the fundamental problem. So the IP layer provides logical addressing for internetworking. So a packet goes through the internet, arrives at my border gateway, and now that gateway needs to do the last mile, needs to forward that packet to the intended device, the final device, the destination device. The problem is that that network doesn't work anymore on IP, but it works on Ethernet. So how do we assign the destination IP address to a destination MAC address? And this is where the ARP protocol comes into play. It creates a mapping between an IP address and an Ethernet address. So how does it work? We got 3 scenarios when ARP is needed. So local delivery, the destination IP is on the same subnet. Gateway delivery, where the destination IP is on different subnets, and we need the gateway MAC or the next hop MAC. And router forwarding, where the router needs the next hop MAC address. So here we got a few examples. This is a router ARP for the next hop. This is an ARP for the gateway. So the packets comes to the router, needs to figure out who's the destination device for that packet. And here host A wants to send a packet to host B. On the IP level, it needs to figure out the MAC address for host B. And the way ARP works is extremely easy. We got the pairs of sender and target, MACs, and IPs. And the way it works is we got an ARP request, which is broadcast, and it's initiated by a host, by the sender host that wants to figure out the destination MAC address to put onto the packet for the switch to be able to route that packet. So for example, if host A needs to send a packet to 192.168.1.200, host A checks the ARP cache. So we maintain a table of all the translation that we saw before. There's no entry. Host A sends a request to the broadcast MAC address. And what the ARP request contains is literally a message in the form, who has this IP address, tell it to me, tell it to my IP address. And the target MAC, so this, it's going to be all zeros because we don't know yet what it is. And since this is a broadcast frame, all hosts on subnet receive this frame, but only host B, which has this IP address, should respond. And so at this point, host B knows the MAC address of host A because it's inside the ARP request here. So host B can reply unicast, meaning it doesn't need to send a broadcast frame. It can send a unicast frame only to host A, where host B recognizes its IP address in the ARP request. Host B creates an ARP reply with its MAC address. Host B sends a unicast reply directly to host A, and host A receives reply and updates its ARP cache. Host A can now send packet to host B using the correct MAC address without having to ask him again until that ARP cache expires. And here we have the complete ARP exchange in the example that we just saw. So the ARP cache avoids repeated broadcasts for the same destination, improves network performance, and reduces traffic because this ARP request and reply takes a round trip to end, and reduce processing overhead on all hosts. So it's basically a table that contains mappings between IP addresses and MAC addresses with an age that is assigned to that cache entry. And here we got basically three entry types, where we got a dynamic, which is learned through this ARP request and reply process. Then we can install entries manually. And then we have incomplete entries, where we basically have an IP address where we still don't have a MAC address because we're waiting for a reply. This is how we can inspect the ARP cache inside a Linux machine, but we're going to see that into the coming lectures. We also have this concept of gratuitous ARPs, where a host announces IP address ownership and allows all hosts that receive that ARP request to update their caches, to elect to update their caches after changes, and it's used in failover scenarios. And it's typically used in both processes, so announce the presence and detect conflicts. IP changes, where we change the IP address of a host and that host broadcasts it's this change. Virtual machines, high availability. There are quite a few scenarios with this gratuitous ARP are used. The fact that a host sends a gratuitous ARP doesn't mean that all the hosts that receive a gratuitous ARP has to do something with it. So that's up to the host, to the implementation, to either honor that gratuitous ARP and update the cache or do nothing with it. Now moving up the ladder, we got layer 4, which is usually called the transport layer into the ISO OSI stack, and it basically handles end-to-end communication between application, process-to-process delivery using port numbers, error detection and correction, flow control, congestion control, and connection management for connection-oriented protocols. So we're going to see with TCP what that means. So the transport layer key function is multiplexing, demultiplexing, reliability only for TCP. We're going to see it's a transport layer protocol, flow control, and congestion control. So we saw layer 2 works with MAC addresses, layer 3 works with IP addresses, layer 4 works with ports. And the ports identify an application within a system, within a server, within a device, within a... And we got well-known ports that go from 0 to 1K, register ports that go from 1K to 50K almost, And then we got dynamic and private ports, which go from 50K to 64K. And those are called ephemeral client. And the reason why we go up to 64K, we're going to see that both transport layer protocols, so UDP and TCP, those ports are represented into a 16-bit number. Here we have common well-known ports, and we're going to go through most of these during the next lessons. So now with layer 4, we can introduce a new concept, which is the socket. And the socket is basically the combination of IP address, port number, and protocol. So here, for example, we have a TCP connection. So the protocol is TCP. We open up a port 54.32.1 on 192.168.1.100. So this is the source port that is generating a connection to a server on port 80. So we know that from the previous table that this is a web server. So port 80 is HTTP, which is the protocol that it's used for web servers. So we generate an ephemeral port from the client, or a random port from the client, to send a packet onto that destination port, which is 80, a well-known port. And this opens up two sockets on both the client and the server. And we got different socket types. We got TCP sockets, connection-oriented and reliable. UDP sockets that are connectionless, so there's no concept of connection of session. It's just one packet going in, one packet coming back, and it's a best effort kind of delivery. Now we got row sockets, which are Ethernet L2 sockets. So let's talk about the first transport protocol, which is called UDP, and stands for User Datagram Protocol. It's connectionless, there's no connection establishment, no delivery guarantees, minimal protocol overhead. You can see we only have a source port, destination port, length of the packet, and the checksum on the header. It is extremely fast, low latency, high throughput, and it's stateless, so there's no connection state maintained. And it's best used for like streaming application where you don't care about losing some packets. Since we don't have any delivery guarantee, think about voice over AP, think about Netflix, think about all those protocols. In theory, they should use UDP. In practice, they use TCP. And so UDP use cases is DNS queries, DHCP, streaming media, although most of the actual streaming runs on TCP, online gaming, SNP, voice over AP, signaling, and the list goes on and on. Then we have the other protocol, which is a transmission control protocol. It is connection oriented. We got a three-way handshake to set up the connection. We're going to see what that means. It is reliable. It has flow control, so it prevents receiver overflow. We're going to see that we have a sliding window of packets that we're going to go through. It has congestion control, so adapts to network conditions, and it's full duplex, so allows for bidirectional communication. And here we got the source port and destination port the same way that we have for UDP, and now we have a sequence number, an acknowledgement number, the flags, the window for the flow control, a checksum, a urgent PTR, and some variable length options. And we can see that the UDP header is 8 bytes, while the TCP header is 20 plus bytes. So it's not as fast as UDP because we got all this information, all this overhead, but it has guaranteed delivery and ordering of packets. And so TCP use cases is web browsing, email, file transfer, remote access, any application that requires reliability. And here we have a table comparison between UDP and TCP. When do we choose UDP? Speed is more important than reliability, real-time application, simple request response like DNS, and broadcast and multicast scenarios. We're going to use UDP also for tunneling on VPNs. And here we have a few protocol selection examples. Doesn't really matter because the selection is done for us whenever we use a service. Now we need to understand a little bit more about TCP. Since it's a connection-oriented protocol, we have multiple stages of that connection. And those stages are closed, listening, seen, sent, SYN received, established, fin wait 1 and 2, close wait, less ACK, and time wait. So we got a few key phases. We're going to go through all these steps with some diagrams in a bit, but we got some key phases, which is connection establishment, where we got the three-way handshake. So the client initiates the connection, the server replies, the server receives that, sends an acknowledgement, and the client sends an acknowledgement back for that packet. Then we have data transfer, so bidirectional communication, where for each packet or each chunk of packet, the server sends back an acknowledgement, and then we got a connection termination, which is a four-way handshake. And this is what it looks like for the connection establishment. So the client sends a SYN packet with a sequence number. The server replies with a SYN-ACK with a new sequence number and acknowledges all the packets that have been received before plus 1. So it means that the acknowledge also covers this first SYN packet that has been received. And then the client will send a new ACK for this SYN-ACK, acknowledging all the packets that have come before with a sequence number plus 1. And so here we establish the connection and the data transfer can begin. So the purpose of each step is the SYN client request connection sends initial sequence number, the SYN-ACK the server acknowledges and sends its sequence number, the client acknowledges the server sequence number, and at this point they're both aware of each other and they can start transferring data. Now if you want to terminate the connection, the client sends a fin request. The server replies with an ACK to that fin request and sends a fin himself, and the client acknowledges that fin request, and at this point the connection is closed. This time wait state that we see here is essential to ensure that all packets from the connections are gone, because here, while the client sends a fin, the server might be streaming response packets from a previous request. So it prevents port reuse issues, meaning that the client and the server cannot reuse the ports that they're using until the connection is closed or until there's a timeout. And this typically depends on the operating system implementation. And this can cause port exhaustion in high traffic scenarios, because if we got high traffic, a lot of connections, we can run out of ports pretty fast. And so it's important to tune that time wait at the operating system level if we face a high traffic scenario. A little bit more information about sequence number and acknowledgement. So the purpose of sequence numbers is to ensure reliable and ordered delivery. So there's no guarantee that the network is going to deliver the packets in order from the client to the server, but with a sequence number, the server can now reorder those packets himself. He can detect duplicate packets, enables flow control, and supports retransmission. So here, for example, the client sends sequence number 100 with 50 bytes, and the server acknowledged 150 bytes, so meaning that acknowledged all the data that has been sent so far. Now, the client then sends a sequence number 150 with a length of 30 bytes, and so the server acknowledges up to 180 bytes, so all the previous transaction. So the sequence number is a position of the first byte in a segment, so in a TCP packet. The acknowledgement is the next expected sequence number. We can have cumulative ACKs, so acknowledge all bytes up to the ACK, to the acknowledged number, and the window size, so how many bytes and how many packets are acknowledged within an acknowledgement, is basically a flow control mechanism. Now, we can understand how network address translation and port masquerading works. So masquerading is the type of net that maps multiple private IPs to single public IP using port translation. So for example, suppose here that we get a private network with PC1, 100, 101, 102. The router keeps a network address translation table where router says, okay, the internal device .100 has a connection to port 80 of some device using ephemeral port 1024. I'm going to map that 1024 port to a port 5000. And same thing goes for all the other ones. So when for example, PC1 wants to reach an HTTP server on the internet, it generates an ephemeral port 1024 for that connection. The NAT router is going to change both the IP address and the port, and the source port with .1, so its IP address, and a network address translation port, which is 5000. And the destination port is not going to be changed because the masquerading NAT falls into the destination NAT family of network address translation. Now, when the server replies back, the destination port is going to be 5000, the IP address is going to be .1. At this point, the router knows that by doing a reverse lookup on this NAT table, that all the packets that are destined to 5000 are really destined to .100 1024 port. So it generates a new packet out of the response packet to PC1. So there are a few key points here. Each internal connection gets unique external port. The return traffic is matched by destination port, enables multiple hosts to share a single public IP because they all share the .1 here, you can see. And works with both TCP and UDP because we don't really care about the nature of the protocol as long as we can use ports. We got a few port allocation strategies. We got static port mapping, which is a fixed internal and external port mapping. It's configured manually. It's used for servers behind NAT. And we have to implement port forwarding rules. While we have dynamic port allocation, which is the most used one, it assigns ports in order or randomly, or port ranges, or it can reuse ports. We have to still be careful about port exhaustion issues because we still have roughly 65k ports per public IP. High traffic server can exhaust port. We got a few solutions like multiple public IPs or connection pooling. And this is how the connection tracking system for network address translation works. But we're going to see all the details about this when we're going to talk about firewalls. Another protocol that it's interesting to understand is Internet Control Message Protocol. It's a network layer protocol, so it works on layer 3. It's an integral part of the IP suite, and it's used for error reporting and network diagnostic. It is carried directly inside IP packets. That's protocol number 1. It's not a transport protocol. There's no port concept. And it's connectionless and unreliable, no guarantee of delivery. And this is exactly what it aims to figure it out if there's delivery or not. It's essential for network operation. And this is what it looks like. We got the IP header, the type of ICMP message, the code, the checksum, message-specific data, and the data if this packet is related to an original packet, for example, a TCP packet that failed to be delivered. For example, TTL ran out or we couldn't find that port open. We got a few common ICMP message types like echo reply, echo request. This is what we use when using the ping command. Destination unreachable, redirect, time exceeded, TTL, parameter problem, timestamp, time synchronization issues. And here we make a distinction between error and informational messages. Now, to understand the time to lib in IP headers, what we need to understand is that the TTL prevents infinite routing loops. It limits the packet lifetime in the network, and it's decremented at each hop of the network, so at each router, and the packets gets dropped when the TTL reaches zeros. And usually the initial value depends on the operating system that generated that packet. It can be either 64, 128, or 255, which is the maximum available. And when the TTL reaches 0 at a hop, the packet gets dropped and the hop sends back an ICMP time exceeded packet to notify the sender saying, hey, this thing got canned. And this is how the TTL works in routers. We got a host A that generates a packet with TTL 64. That TTL gets decremented by R1, decremented by R2, decremented by R3, and reaches the final destination with TTL equal 60. And so when the TTL expires, the router receives packets with TTL equal 1, the router decrements TTL to 0, the router drops the packet, and the router sends ICMP time exceeded to source, which is type 11, and the source now can try and resend that packet or report an error message to the user. And by using this mechanism of TTL, we can implement a traceroute tool, where a traceroute tool purpose is to discover the path packets take to a destination, identify each router along the route, measure round-trip time to each hop, and troubleshoot network connectivity and performance. So the traceroute strategy is fairly easy. It sends a packet with incrementing TTL values. So TTL1 for first hop, that hop it's going to drop the packet and send an ICMP packet back with its IP address. And at that point, the guy that sent the packet with TTL1 can take notes and say, okay, so this packet got dropped here, so it means that the traffic goes through that hop. And then it does the same thing with TTL2. So the first hop now can forward that packet, and it reaches with TTL1 on the second hop. It decrements TTL0, sends an ICMP time exceeded packet back, and so on and so forth until the packet reaches the final destination, and it builds the complete path from ICMP responses. How do we know when we reach the final destination? So Unix traceroute uses UDP to unused ports, which are likely not to be in use by the final host. And when we receive an ICMP port unreachable, this indicates traceroute that it reached the final destination. And it's different from intermediate routers sending time exceeded, because the final destination does not decrement the TTL. If it receives a packet with TTL equal 1, that's fine. It's not going to decrement or do anything because it's the final destination. That packet doesn't need to go anywhere else. And this is what the output of the traceroute command looks like. Again, we're going to go over this during the next lectures.